So your homework last night, let's take a look at that. Don't forget your equation was right there at the top. So all you needed to do was figure out if this was growth or decay, what the rate is, and what the amount of time intervals that were passed. So in this case, the bad investment starts at $250. That's your initial value. You're going to multiply that times 1, and it's losing, so that's decay. 2%, 0.02. Make sure you put 0.02. If you didn't, it's going to throw off your answer. And how much does he have left after 16 years? So to the 16th power. There's what you should have set up. If you had a calculator on you, hopefully you did. And if not, hopefully you found one online or used your cell phone. You plug that in. How much money is left? Well, it would be $180. And then we have to round. We're rounding this to the nearest cent because that's what we do with money. So it's 0.949, which means it rounds to 95 cents. The next one, we're talking about 5,000 bacteria on a public restroom. Ew. All right. So how much of that is on the door handle? It's increasing at a rate of 33% per hour. How many will there be after 4 hours to the nearest bacteria? So we've got y equals, that's our final value. Our initial value is 5,000 bacteria. And then it's increasing, so times 1 plus 33% would be 0.33. And we raise it to the 4th power because there's 4 intervals going by. So in your calculators, you should be typing in 5,000 times 1 plus 0.33 to the 4th power. And it wanted it to the nearest bacteria. You've got 15,645.0. So it's 15,645 bacteria. That's disgusting. Next one. 722 JCHS cell phone subscribers, growing at a rate of 1.8% per month. How many subscribers after 9 months to the nearest student? So we start off with an initial value of 722. It's growing, so 1 plus. Be very careful with the 1.8%. I suspect many people would have a little slip up with this one because when you move this over twice, remember you can do that because you're dividing by 100 as a decimal, even though there's a decimal point in there, when we get rid of the percent and we divide by 100, it's 0.018 as a decimal. Make sure you check that. If you didn't have that rate, then your final value is going to be off. You should put in your calculator 722 times 1 plus 0.018 and raise that all to the 9th power. You should get 847.748830,989. You're rounding it to the nearest student. Even though our rules of rounding would tell us that that 0.7 normally rounds up, not enough time has gone by to get to that next whole person. So we have to kind of break the rules of rounding. The whole amount of students we have is 847 students. And our last one for homework last night. When doctors prescribe medicine, they must consider how much the drug's effectiveness will decrease as time passes. For a certain medicine, each hour the drug's effectiveness decreases by 5%. Each hour with an initial dose of 250 milligrams. How much will be left after 6 hours? All right, so we're talking about decreasing. So that indicates to us that we have exponential decay. Our initial dose was 250 milligrams. We'll multiply that by 1 minus the rate. In this case was a 5% decay, so 0.05. And we want to know how much we have after 6 hours, so to the 6th power. So that should have been your equation. And then you would type it into your calculator. And if you haven't already, hopefully you have your calculator in your hand right now. You're typing it all in, and after you type that in and you hit enter, it says that there is 183.7729722656. It didn't say where to round. And in this scenario, it's not money, it's not people. So in this case, I'm going to leave this as the whole decimal that they gave us, 183.7729722656. It didn't tell me to round, and that would be in milligrams. All right, on the back. How can you tell if you have exponential growth or exponential decay? By looking at the graph. If you're looking at a graph, growth is going to happen when it's moving upwards from left to right. And decay is going to be just the opposite. That's when your graph goes downwards from left to right. What about when you're looking at the table? When we're talking about a table, we're talking about looking at something like this. And you'll know it's growth because the y values will increase. It's growing. And for decay, just the opposite. The y values, decrease. And lastly, with the equation. So when we're talking about the equation, we're talking about y equals a times b to the x power. Remember that b is comprised of the 1 plus the rate or the 1 minus the rate. When we're looking at this, that base, b, will be greater than 1 when we have growth. You'll see that in the exponential growth and decay formula when you have the plus. When you have a times 1 plus r to the t power, you're going to end up with a number bigger than 1. 1 plus the rate will always be larger than 1 when you add them together. And that's going to indicate that the exponential function is growing. On the other hand, when you have decay, that base value, that's going to be some number between 0 and 1. Like 0.3 or 1/3 or 0.7. So that's going to happen when you have a times 1 minus the rate. When you take some value away from 1, you're going to get a number smaller than 1. And when that happens, that indicates decay. So for example, this would be something like y equals 2 times 1/2 to the t power. There's exponential decay. Our initial value is 2. It is getting cut in half each time. When it was growth, that would have been something like y equals 4 times 2 to the t power. Well, now we're starting with 4, and it's doubling every time, and that base of 2 is going to make it grow.